If you have practiced with past papers, probably you have noticed that in paper 1, most likely you're going to have one question where you have to prove a statement using mathematical induction. One of the possible type of statement to prove is one with an inequality, and that's what we are going to solve now. We are going to use mathematical induction to prove that for any positive integer n, 2 times n, all of that factorial, is greater or equal than 2 to the power of n multiplied by n factorial squared. While we do this, I'm going to assume that you know how mathematical induction works, so we're not going to review that here. And I'm also going to assume that you understand and can work with factorials. We begin by proving the base case, that is, for the first possible value of n, we prove that the statement is true. Since this says over here that this is for n belonging to the positive integers, our first possible value is n equals to 1. So we're going to check that the statement is true for n equals 1. In the left-hand side, we have 2 multiplied by 1 and then all of that factorial, which is just 2 factorial, which is just 2. And on the other side, we have 2 to the power of 1 times 1 factorial squared. So that's 2 times 1, so this is 2. And yes, it's true that 2 is greater or equal than 2, so the base case is 2. Now, we need to assume that the statement is true for a number, let's say n. And so assume true for n. So we are assuming that the statement is true in this case. And we want to use this case to prove that it's true for the following number. So prove it's true for n plus 1. So the statement we are trying to prove is that 2 multiplied by n plus 1 and then all of that factorial, so instead of n I wrote n plus 1, is greater or equal than 2 to the power of n plus 1 multiplied by n plus 1 factorial and then this number squared. This is what we want to prove. So I'm going to start with the left-hand side. So with 2 multiplied by n plus 1, all of that factorial. And I'm going to work my way to showing that this expression is greater or equal than what we want for the left-hand side. And of course, on the way, we are going to need to prove what we assume. That's why we assume it 4. So what does it say over here? So it says that 2 is multiplying n plus 1, so we have 2n plus 2, all of that factorial. And by the definition of factorial, this means that we have 2n plus 2 multiplied by 2n plus 1, so one number less, and then multiply by 2n, and I could keep going like that, but I'm just going to write here the 2n factorial. And the reason I'm doing that is because if you see over here, this 2n, all of it factorial that I got on my expression is also on the expression that we're assuming to be true. So this is going to be useful. We can say by the inductive assumption that this last factor, 2n all of that factorial, is greater than or equal than 2 to the power of n times n factorial squared. This is the assumption we have over here. So now I'm going to rewrite my expression, but now I'm going to repeat the same factor, 2n plus 2 and 2n plus 1 multiplied. But instead of writing the last factor, I'm going to write something that is less or equal. So I'm going to write that what we had in the previous line is greater or equal than, and now I write 2n times n factorial, all of it squared. So look here, this is very important. This is the property we are using over here. Let's say we have a being multiplied by c, and we know that c is something positive. And then we also know that A is greater or equal than some other expression B. So we can substitute in our expression B. So we can write B times C, and we're going to have the greater or equal sign over here. This is what we did over here. We kept the first two factors, and we substitute the third one by something that we already know that our original factor is greater or equal to it. Notice that we are getting closer to what we want to get. For instance, in the expression we want, we need to have 2 to the power of n plus 1. And so far we have 2 to the power of n. This is not very hard to fix because actually you can take 2 as common factor from the first factor 2n plus 2. So we are left with 2 multiplying n plus 1 multiplying 2n plus 1. Then multiplying 2 to the power of n factorial square. And then we have over here the factor of 2 that we were missing, so we can collect factors of 2 together and write that this is 2 to the power of n plus 1, and then we have n plus 1 times 2n plus 1 times and then factorial square. Okay, so now let's look at the rest of the expression we want. We want this n plus 1 factorial, all of it squared. But notice what we have over here. Well, first of all, when we have n factorial squared, we can write that this is n factorial times n factorial. And the reason why I do that, because then when we also consider the factor n plus 1, we have multiplying outside, this one here. This, we can collect together the n plus 1 and the n factorial and write that this is n plus 1 factorial. So let me write what we have over here once we collect those terms. We have 2 to the power of n plus 1 as we wanted. Then we have n plus 1 factorial. Then there is a factor 2n plus 1. And then there is another n factorial. If what we have over here, 2n plus 1, was just n plus 1, then we'll be done. Because we'll put together that factor with the n factorial, and we'll have the n plus 1 factorial, and then we could write n plus 1 factorial, all of it squared. But, well, so what we want here is just n plus 1. But 2n plus 1 is greater or equal than n plus 1, because 2n is greater than n. And remember that we just want to make sure that the expression we started with is greater or equal to what we want at the end. So it's okay to substitute this by this is greater or equal than n plus 1, 2 to the n plus 1 is the same, n plus 1 factorial is the same, but then instead of writing 2n plus 1, I just write n plus 1 times n factorial, and this is 2 to the power of n plus 1, n plus 1 factorial, all of it squared. So, as we wanted to, we proved that the statement is true for n plus 1, since we proved that 2 multiplied by n plus 1, all of it factorial, is greater and equal than 2 to the power of n plus 1 times n plus 1 factorial, all of that squared. So we just need to conclude now. So, since the statement is true for n equals 1, that was our base case. And then what did we do? Well, we assumed that it's true for n. And assuming it's true for n, we proved it's true for n plus 1. Then we did the 2 steps of a mathematical induction. We proved the base case, and we proved that one step implies the following. Then we can conclude by mathematical induction. Then let's see here, abbreviating. The statement is true for all n positive integer. And that was what we wanted to prove. I just need to correct a mistake I made on minute 7. Over here, I'm over here at this step. I'm miswriting the other copy of n factorial and was over here. This copy should be here. I just forgot to write it, but actually I did write it in the next step when we kept going the steps afterwards. So just needed to correct that.